All right, lecture number 4. So in this lecture, we talk about supplementary cementitious materials, okay, such as flash and slag. So SEMs has been used by human beings for many years, thousands of years. So this is the very famous Pantheon, also called the Temple of Gods. So it made in 128 AD. The Pantheon has hold the largest dome diameter, so 43.2 meters for 1800 years. Okay, so the Pantheon was made by the ancient Roman engineer using volcanic ash, belong to one type of supplementary cementitious materials. In the US, the famous Golden Gate Bridge in San Francisco is also made by slag and cement. Okay, so this is was built in 1930s, so almost 90 years ago. So SEM, also called mineral mixtures, it is to replace part of the cement. So cement together with mineral mixtures, we call them binder or supplementary cementing materials or supplementary cementitious materials. Okay. So it is a materials like when used together with Portland cement, will enhance the performance of concrete through two possible activities: hydraulic or pozzolanic, sometimes both. So here are the picture of the major SEMs from flash. So for flash, we have class C flash and class F flash. Okay. So the one on the left is class C. The first one from the left is class F. Okay. The difference between these two types is the percentage of calcium oxide in it. Okay. The white powder is metakaolin, okay, also called calcium clay. Okay. So that's the kaolin clay, by heated up to high temperature. Silica film is the third one, has a bluish color. This one also red color, white color is the slag. Okay, so slag is another commonly used SEM. It's coming from the byproduct of steel production. And the last one is calcined shell. So shell is a sedimentary rock. So calcine means heat up to get rid of the water and CO2. Okay. So similar to metakaolin. So pozzolans is the siliceous, means it has reactive silica oxide. Sometimes also have reactive aluminum. So it is siliceous or aluminosilicous materials. Okay. In a very fine form, similar size as Portland cement, around 10 micrometer, 10, 20, sometimes even smaller. Okay. Together with moisture. Okay, so water has to be there with pozzolans and also calcium hydroxide. So these three will react slowly and it will form CSH. We talked about pozzolanic reaction, the chemical reaction equation before. Okay. We'll touch that in a moment too. Natural pozzolans is a natural materials, has pozzolanic properties. Okay, including metakaolin, rice husk ash, volcanic ash, and also calcium shell, and also calcium clay. So this is natural pozzolans. We also have pozzolans coming from industry byproducts, such as flash and slag. Okay, so for example, the coal ash, also called flash, a power plant burning a lot of coal to generate electricity, and also steel manufacturing, producing cast iron, silica metal. Okay, so this industry activities will generate flash in the case of coal burning power plant, slag in the case of steel manufacturing, silica film for silicon metal. Okay. Before, we need to dump all this byproduct into landfill. Okay, and it will generate a lot of environmental issues and also increase the recycling cost by quite a lot. Okay. The amount of this byproduct is huge. For example, we generate hundreds of millions of flash worldwide, and also slag. If we can use these materials to replace Portland cement, so we can reduce landfills, reduce the recycling cost, and also reduce the energy, and also reduce the CO2 emission coming from the production of cement. So we can dispose these waste materials as concrete aggregate, such as sand, or for road-based construction. But this is a very low value use because it does not utilize the pozzolanic and cementitious potential for these materials. Okay, if we can replace materials, replace cement using these materials, it will has much higher value. Okay. So we can blend these materials with Portland cement or use as mineral mixtures. So whenever a pozzolanic ore and cementitious byproduct can be used as partial replacement for Portland cement, then it will represent significant energy and also cost savings. Okay. So that's the goal for using SCMs. And we know from previous lecture, this is pozzolanic reaction. We have calcium hydroxide coming from reaction of C3S and C2S. So these two are the major compound in Portland cement. And pozzolanic reaction is flash, silica film, slag. Okay, we call that pozzolans. They will transfer calcium hydroxide together with water to generate more CSH. Okay. So compared with calcium hydroxide, CSH is stronger. And also for this reaction, the total volume of solids also increase. So the volume increase for pozzolanic reaction. So that means the volume of empty voids, the pores, we call that porosity in concrete, also reduced. So that will translate into higher strength and better durability. The reaction is also slow, as I noted here. It takes several months, to achieve its full potential. So we need continuous moisture curing for this slow process for pozzolanic reaction. So again, we need a continuous moisture curing because the reaction is slower. The reaction is also temperature sensitive. Higher temperature, it will react quicker. Okay. Under steam curing, higher temperature, moisture, steam. So then the reaction speed will be much faster. The pozzolanic capacity of different type of SCMs, which is tested by direct reaction of calcium hydroxide and monitor how much calcium hydroxide can be consumed by different type of SCMs. Okay, as we can see, the difference are quite big. For slag, we also call that blast furnace slag. So it consumes 40 milligram of calcium hydroxide for each gram of slag. Silicon film is 10 times of that. For flash, even higher, metal coating is approach to 1,000. So 1,000 milligram is equal to 1 gram. Okay. Then let's look at each of these commonly used SCMs. The first one is flash. It is by far the mostly used SCMs, right? 250 million tons a year. I think it is not most recent information. I think nowadays, for China alone, each year it will generate 500 million tons. Okay, and China account for about 50% of the total flash generated worldwide. Okay, in Hawaii, we have around 300,000 tons of flash, which is generated in a local power plant called the EES. I think it's in the Kapolei area. Okay, 300,000 tons of flash each year in Oahu, but we cannot use this flash because it has some impurities which prohibited them from being used in normal Portland cement concrete. Okay. We have done some research here at the concrete lab. Over the past 10 years, we try to use some low quality SCM, such as the flash from AES power plant. And also we try to use some other type of SCM, such as red mark, which is the byproduct from aluminum production process. We have been very successful by doing that. Okay, so we'll talk about that in future lectures. So flash, again, is produced during the combustion process of coal in a coal burning power plant. And flash melted at very high temperature and quickly cools down, okay, and into different type of materials, such as flash and bottom ash. Okay, flash is one type of the materials from this process. So the fused matter quickly transported to lower temperature zone and it solidified, and we have spherical particle of glass. Okay, so the key here is, first of all, we have high temperature and the coal byproduct is melted, and then the temperature drop down quickly, and then this calcium oxide, silicon oxide, and aluminum oxide will become solid again as glassy materials. Okay, so only by doing this, the flash will become reactive. Okay, we'll see it's the same case for other type of SCM, such as slag. The cost of flash is depending on location. Okay, typically, it will be cheaper than Portland cement, around 50% the cost of Portland cement. But here in Hawaii, because we cannot use our locally produced flash, and we need to buy the flash from other places. So in Hawaii, the flash cost is similar to Portland cement, sometimes even more expensive. The size of flash is similar to Portland cement, around 10, 20 micrometer. Okay. But the shape is almost perfectly spherical. So round shape, sometimes also partially hollow. Okay. So most flash particles are glassy. Okay, so you can think glassy materials as reactive. So glassy materials is caused by quickly quench the high temperature melted materials into low temperature. As a result, the oxide become reactive. We also call that glassy. So glassy is good. That means reactive. In the US, we have two major types, class C. So if the calcium oxide percentage is more than 10%, it will be classified as class C. Okay, so class C flash coming from low rank coals, okay, with limestone, which is calcium carbonate as impurities. Class F, when the calcium oxide percentage is less than 10%, so we call that class F, it coming from higher rank coals. And these two classes of flash behave differently in concrete. Okay, so look at class C flash. So class C flash have mostly calcium and aluminum rich glass. Okay, the reaction of class C flash is faster compared with class F. Okay, so crystalline component. So when we talk about crystalline component, it normally means it is not very reactive. So that's the opposite of glassy or reactive component. Okay, so crystalline component is not very useful because we cannot use it as pozzolanic materials. So calcium sulfate or anhydrate, okay, is one type of impurities. Sometimes we also have A-light or B-light. So A-light and B-light is another name for C3S and C2S. For class F flash, it has less amount of calcium. So it has a siliceous glass. Reaction is more slowly compared to class C. Okay, so this shows the crystalline phase, such as quartz, moonlight, and some other oxide. So high calcium flash have little use in European countries, but low calcium ash or class F flash is widely used because it is easier to control the reaction due to lower calcium content. So in summary, class F flash has mainly S, silica and aluminum. Okay. For class C, it may have both pozzolanic and cementitious property. So cementitious property means because class C flash has more calcium oxide, okay, and sometimes it will generate CSH by itself. And the flash from our Hawaii power plant, AES flash, is not allowed to be used due to high sulfate content. Okay. In the lab here at UH, we have been successfully used the flash from AES power plant to make very high quality concrete. Okay. So we call that geopolymer concrete. So this concrete is different from what we discussed here. It does not use any Portland cement. So flash and slag does not replace part of cement. It replaces 100% of the cement. So we use some admixtures to activate the potential for these materials. so no Portland cement is needed. Okay, the performance is very good. So I will have a guest lecture for us. It's Riza. Riza is my postdoc research fellow here at the concrete lab. So he's in charge of the geopolymer concrete project. So I will invite Riza to give us a lecture about geopolymer concrete.
So from the fly ash from the power plant, from the research, what was the actual percentage that we could use?
100%.
You could use 100%, but
Yes.
you can't use it for like structures, right? So maybe like sidewalks, like low impact structures.
You know, the standard said when the sulfate content in flash
Yes.
is higher than a certain percentage, it is not
Yes.
allowed to be used in Portland cement concrete.
Oh.
So you know, the contractor cannot use for any, as long as it's blended with Portland cement. Okay, so the reason for that, as you may can guess, is the potential for sulfate attack. Okay,
right.
So because it has too much sulfate content.
Yes.
However, in this new geopolymer concrete, we do not need to worry about sulfate attack at all because it does not have any AFM and AFT, no etching gas formation possible. So we no need to worry about the sulfate attack. So we can use, you know, our local AES flash in geopolymer concrete because of this reason.
That makes sense. Thank you.
Okay. Thank you for the good question. So flash mostly has a spherical shape, as we can see from here. Some particles are also hollow inside. Typical size around 10, 15 micrometer. No, H power is not H power. We also tried using H power ash, but H power ash is not flash sometimes. It burn some trash such as furniture. So not only coal, but also some other materials. But we do try to use H power ash in our geopolymer concrete. And we can replace Portland cement concrete using H power ash up to 40%. Okay.
Because I thought fly ash was specifically made from coal as the byproduct.
You mean the H power ash?
Oh no, H power ash is all trash. So that one is super contaminated. So I would never want to use it for fly ash. But I thought when we talk about fly ash specifically, I thought it was a byproduct of coal.
Yeah, coal burning process. Yeah.
Right.
But we can use the H power ash up to 40%, 30, 40%. I use some flash and some slag. You know, still no Portland cement is needed to make very good concrete. So we have done that in the lab.
So can I follow up on that? So we're talking only, so far we've only been talking in Hawaii about the fly ash that's coming from the coal plant, but that coal plant is scheduled for decommission within, I don't know, about a year and a half. I think about a year. So then there would be, what would be the source for fly ash here?
Yeah, right now all the flash is imported from other places, like mainland US, China, I don't know, Korean. You know, because anyway, we cannot use our AES ash due to the high sulfate content. So we buy all the Portland cement, all the flash, slag, we import it from other places. We do not produce here in Hawaii. Yeah.
Oh, I see. Okay, I understand now. Yeah.
Yeah.
Because it's lousy coal, right?
Yes.
Yeah, very high sulfur content. Okay, I understand.
Yes. Okay. So effect of flash on mixing water requirement. we see the picture of SEM. So flash has a ball shape. So it has a ball bearing effect, which can facilitate the mixing with other particles. Okay. So here, just show the example by using flash, replace a certain percentage of cement, we can reduce the water requirement. Silica film is coming from production of silicon, ferrosilicon, or other silicon-containing alloys. Okay, so silica film, as we can see, is brutish color powder, much finer compared with flash, so almost 100 times smaller in size. Reduction of course to silicon at very high temperature, so it will produce silicon oxide vapors, and then when it condenses at low temperature zone, it becomes very reactive, these tiny spherical particles containing, again, 9 crystalline silica. So 9 crystalline means glassy or reactive silica. It is industry byproduct, but it's very expensive. So the cost of silica film actually is about 10 times more than Portland cement. So the reason we use silica film in concrete is not to cut down cost, but to enhance the performance, such as strength. For high strength concrete, it is essential to use silica film. Okay. It has significant amount of alkali. Okay. The particle size is very small, so 0.01 micrometer compared to 10 micrometer in flash and Portland cement. Okay. Sometimes these tiny particles cannot be fully dispersed. Then they become like a big agglomerate, so big chunk together. If that's the case, it may cause some problems in concrete, such as alkali silica reaction. Okay, so or ASR. So ASR is another type of sulfide attack, other type of chemical attacks, potentially for concrete. And yeah, we'll talk about it more. It reacts very quickly. Okay, it can increase the strength by quite a lot, and also reduce the permeability of concrete. Okay. So here, compare the particle shape and the size of silica film. The particle size is very small, also spherical shape. So this is a cement, flash, spherical shape, but similar size to cement. We also have a so-called ultrafine flash, but still is much larger in size compared to silica film. Okay. So here I mentioned feeder effect will increase the particle packing density. That's one of the reasons why silica film can enhance the performance of concrete by that much. Let me share. The reason why silica film can enhance the concrete performance due to several factors. So one of them is called the feeder effect. We can see from the picture here, the particle size of silica film is so small. Okay. So if these are cement particles, okay, and silica film particles is so small that it can fill the gaps between the cement particles. Okay, so as a result, we can put more solid in the mix by using silica film. So the packing density will be higher. So packing density will be higher. So that will means we can reduce the porosity, the amount of voids in the system. And also we can reduce the size of the pore. We call that pore size. Okay, so all of this will enhance the strength. Okay. Because we can put more solid in the system, the requirement for water may also be reduced. But that is with the help of superplasticizer. So superplasticizer is also called water reducing admixtures. So it makes the concrete more flowable. Okay, we talk about in future lectures. So the strength will be higher. So F prime C will be higher, and also more durable. So that is silica film. So the next one is granulated iron blast furnace slag. Okay, sometimes we just call that slag or GGBS. So granulated blast granulate slag. Okay, so that's the byproduct of iron. Okay, so liquid slag is rapidly quenched. So again, the temperature drops down quickly, and we have this glassy or non-crystalline materials. Okay, which means they are reactive. We call that granulated slag because it looks like a sand particle. Yeah, routinely I can get samples from, for example, steel production plant from China, aluminum production plant. They generate a lot of red mud. Red mud is a byproduct of aluminum production plant. It generates hundreds of million tons every year. Sometimes everything, not hundreds, like 20 million tons every year, and they have accumulated hundreds of million tons of these waste materials already. Okay, so they have no place to landfill it. Okay, so they send us this sample. They want to see if they can use it to make concrete or any type of usage. Okay, so we have done some work, a lot of work actually, trying to test these samples and see if they can be used to replace Portland cement to make geopolymer concrete. So this is slag. So slag has so-called cementing properties, okay, or cementitious properties. So that means it can form CSH by itself. Could be, okay. Could. Okay. The reason for that is because the calcium oxide content is high. For slag, the percentage of calcium oxide is around 30–40%, so much higher than flash. Okay. So slag, because the self-cementing properties, it can be used in much higher proportion compared with other admixture. It is glossy, but also have some crystalline component, which is non-reactive. So for reactive glossy part, it has calcium, alumina, and also silica. Okay, so these three are very useful if they are reactive. All right, so for slag, again, it can form CSH by itself, but the condition is it need to be activated by alkali, okay, such as calcium hydroxide from Portland cement hydration. Or we can add some activator, use alkali, such as sodium hydroxide, like what we are doing in the lab, okay, to activate its potential for hydration. So slag has different grade, as you can see here. It just depending on the so-called activity index, which is very simple. Activity index just calculated by the ratio of the strength of two samples at 28 days. So one is with 50% of slag and 50% of cement. Another one is the control mix, means 100% of cement. Okay, so if this ratio is 0.8, then we call that grade 80. So 80% compared to 100% cement. The price of slag is similar to cement, but again, it is highly depending on location. Okay, so if the city has a big, steel production plant, then the price of the slag will be almost zero. Okay, so they want to get rid of this as much as possible. They even give it to you for free. Okay. So slag admixture cement will gain strength slowly, but eventually the strength may be even higher compared to normal concrete. Okay. It will also make concrete impermeable, reduce the permeability, reduce the pore size. So it is beneficial if the concrete is used by the seawater. We need to worry about the chloride entry, corrosion of the steel. Okay, so we may consider using slag to reduce the permeability of concrete. Okay. So flash, slag, and the silica film is the three major SCM used. Okay, then let's look at some minor, less used materials. Okay, metakaolin. Metakaolin is kaolin clay dehydroxylated, so get rid of hydroxide. Okay, by heating to 600 degrees. Okay. It is very fine materials, 0.5 to 5 micrometer. The surface area of metakaolin is very, very high. Okay, so as a result, it can react very quickly. Okay. It can reduce the permeability, make the concrete impermeable, and also can reduce the alkali content in concrete. So when ASR or alkali silica reaction is a concern, metakaolin is a good choice. If we have a lot of rice, so rice husk ash can also be used as SAM. But the rice husk need to be burned first, as you can imagine. So high temperature, then cool down quickly, then the oxide will become reactive or glassy. So after cool down, the rest Casca ash must be grounded to smaller size, very fine particles. Okay, that will also have to gain some pozzolanic activity. Okay, silica is the major oxide reactive materials in rest Casca ash. Okay, and also rest Casca ash has cellular microstructure. That means the surface area is high for this material. So rice, not rice, sorry. Natural pozzolans is not used very widely, of course, depending on whether you have this natural pozzolans such as volcanic rocks and minerals. In Hawaii, we are not allowed by the law to use volcanic rocks. Okay, but in some other places, it is allowed to be used. So except diatomaceous earth, we talk about that is coming from algae. Okay, all natural pozzolans coming from volcanic rocks or minerals. Okay, so during volcanic eruptions, we know the temperature is very high, and again, it has very quick cooling of the materials, the magma. Okay, so that will make the oxide glassy. Okay, so you get the idea. Almost all of these materials, either natural pozzolans or industrial byproduct, the material will undergo a quick cooling process, so it can form a glassy or reactive materials.
What was the reason that we couldn't use Hawaii's volcanic?
They just passed a law,
Yes.
not allow us to use natural resource in concrete materials. Okay, so that's the law passed. They cannot
That's
do it.
specifically for Hawaii?
It is, yeah, our local law for Hawaii only. Yeah.
Yeah.
In other
Is
places,
that-
yeah.
Sorry.
Like here.
Is that law passed because they don't want to consume that, or because there's potential danger using it?
They do not want to consume natural resource. Yeah. That's the
There's a shortage, actually. It was in the paper the other day.
Oh, okay. So there's a shortage of the material. I also thought it was because Hawaii is in that weird like zone where everything is considered sacred. So because they think the like volcanic rocks are considered sacred, they don't want to like touch it as part of being taboo. So it might be a political issue too. But I just wanted a clarification why we couldn't use it, since it is an abundant research that's currently being made.
Yeah, especially in Big Island.
Correct.
Yeah.
Yeah.
In other places like Greece, Italy, it is a lot. People use that volcanic glasses all the time. Some part of Germany. Okay. So we have volcanic glasses of volcanic turfs. These are all coming from volcanic rocks. Okay. So some example of volcanic products used as SCM. Not here. Calcined clay and shell. So clay and shell, they heat it up, dry off the CO2, water, and then the materials become amorphous or reactive. Okay. So aluminum silica structures due to the thermal treatment. Okay. So again, the crystalline structures need to be destroyed by high temperature, by the heat treatment. Okay. That's how we get these materials be reactive. Just another side story, very interesting though. Years ago, I read a proposal to NASA, trying to see if we can use to make some concrete in Moon and in Mars. We call that a lunar concrete project proposal. The reason I think it may be doable is because on surface of the Moon and Mars, they have a very thick layers around 6 feet, layers of soil. Okay, and this soil is the result of impact of surface of Moon and Mars due to meteorite. Okay, the impaction is high speed, very violent, and they also generate this high temperature and quenching. The temperature drop down very quickly. So they have a lot of this glassy silica, aluminum, calcium on the lunar soil. So we have a chemical analysis of the lunar soil, and that's the reason I believe it has a similar performance if we use the lunar soil as SCF. Okay. So this is another type of natural polymers. It's called the diatomaceous earth. It's coming from organic origin, such as algae. Okay, so not volcanic reaction. Okay. So here shows the physical properties, like the size, the surface area, okay, specific gravity for the typical SCM compared with Portland cement. Okay, so silica film, as you can see, is very, very small. Surface area is very high. Okay. And the rest cast ash has a very high surface area due to this cylindrical shape. Okay. Right, this table shows the chemical analysis, the major oxide, okay, of these materials. So if the materials has a lot of calcium oxide, such as slag, okay, then it may have not only pozzolanic properties, but also cementitious property. Okay. And also class C flash, so high enough, 20%. So potentially it has pozzolanic and cementitious properties. But for silica film and class F flash, okay, because a low percentage of calcium oxide, we'll know it may only has pozzolanic property. Okay. So we have mentioned several times, glassy fractions means it is reactive. Crystalline fractions means it is less reactive. Okay, so seeing from XRF, which is normally used to see the percentage of different type of oxide, we cannot see which is glassy and which is the crystalline fraction. Okay. We can use XRD, X-ray diffraction, to tell the glassy part from a crystalline part. Okay, so when you see a lot of peaks, so these peaks only occurs when it is crystalline fraction. Okay. If you see some hump, we call that diffusion band, Okay, so these are the glassy part, which potentially means the materials could be reactive. But some of the crystalline materials can also be reactive, okay, such as the C3A, okay, sometimes C2S and C3S. Okay. Here shows the typical amount of SCM to replace Portland cement. Okay, for example, Class C flash, typically 15 to 30%. Okay, but again, if we use geopolymer or AAM, okay, AAM is for alkali activated materials. Okay, basically they are the same thing. We can use 100% of these materials. Okay, so no Portland cement is needed. Look at how these materials can affect fresh property. It can control the bleeding. So bleeding means the water of the concrete come to the top surface when the concrete is still fresh. Okay. So it can reduce the bleeding and also refine the grain size, make the grain size smaller, okay. Because it transfers a larger calcium hydroxide crystal to smaller CSH, okay, and also reduce the pore size, porosity, okay. It can enhance the workability by reduce the bleeding and the segregation, okay. Okay, enhance the cohesiveness. Can also potentially reduce the amount of water for consistency, but we may need the super processor to achieve the goal. In general, the workability will be enhanced by using SCMs. So again, cohesiveness and workability will be enhanced. But if a material has very high surface area, in the case of res cast ash and silica film, then it may increase the water requirement. Okay. And this table summarizes the effect of different SCMs on fresh property, water requirement, workability, okay, heat of hydration and setting time. So let's look at silica film. Silica film may enhance the water, increase the water requirement, okay, reduce the workability, mainly because small particle size, high surface area. And of course, it will depend on the actual source of the materials. Okay, sometimes it depends on the actual source of these materials. This is a fresh property. This is a strength, long-term strength. Control mix with no flash. The blue is without flash. The red class is with flash. Okay. So normally up to 28 days, the strength of concrete with flash will be lower compared to 100% cement. But later on, the strength will catch up and exceed beyond the control mix. It is because pozzonatic reaction is slower. You need a long time and continuous moisture curing to achieve its potential. So here shows the strength development in cold weather. Okay. So the control is here, the blue curve. Okay. The other three is around 20% of flash replacing Portland cement. So no big difference, doesn't really matter here. We can see again here is up to 28 days. Here, the control has the highest strength. But later on, concrete with flash will catch up. Okay, even in cold weather. But again, it is very important for continuous moisture curing, so continuous water.
For how long would that have to happen?
I will see, up, 2 or 3 months. The longer, the better. Okay. Yeah.
What type of construction is that feasible in?
It not means you do that every day. If I don't think it has a much higher requirement for concrete with flash. It may need a little bit more time of moisture curing, maybe from 5 to 7 days. That's about it. In Hawaii, even you do not provide too much actual water, but because the concrete is so dense, inside of concrete, you still have some of the moisture. Okay. So if it not totally dries out, without providing actual water. Okay. But, you need to remember the more water curing, the longer moisture curing, the better for post-landing materials.
Thanks.
Yeah. And if you have an underwater construction, you don't need to worry about the moisture curing. So water is always there. Silica film. So silica film does not reduce early age strength. So this is in hours, but silica film will enhance this is 7 day, it's 14 day, this is 28 days. Okay, as we can see, silica film will enhance the performance at the beginning. At later age, of course, is even more compared with the control mix. So that is different from flash. So for flash at early age, the strength will be lower compared to control. So durability to thermal cracking, the temperature increase when we use SCM will be lower. The only potential exception may be the silica film. Okay. But most of the case, the temperature rise will be smaller when we use SCM because the post-landing reaction is slower. Okay. So we need to worry less about thermal cracking potential for concrete. Okay. So the rule of thumb is if we use post-landing materials, the total heat will be about 50% less. The benefit of SCM from durability mainly coming from reducing the permeability of concrete. Okay. Because again, we get more CSH. Okay. CSH is stronger, and also we increase the total solid volume due to post-landing reaction. So permeability will also be lower. The pore size will also be small, so smaller pores, lower porosity. So durability of concrete will be improved in most cases. Okay. Sometimes the concrete may crack. You know, for example, if we put too much silica film in the mix, it may have too much drying autogeneous shrinkage, so the concrete may crack. If concrete crack, then durability will not be enhanced. Okay. Typically, mineral mixtures will improve resistance to you know, all type of physical and chemical attacks. Okay. Reduce the permeability, okay, by reduction in calcium hydroxide. So transfer calcium hydroxide into CSH. So this table summarizes the effect of SCMs for hardened properties, like the strengths. Okay. So for flash, we see that, you know, it depends what time you ask. At early age, flash will reduce the strength gain, but the final strength will be higher. Okay. So same thing for slag. Permeability. So all these materials will reduce the permeability, and all these materials will reduce the potential for ASR because they can reduce the hydroxide ions. Okay. Chemical resistance also increased. All right, so in summary, SEMs will remove calcium hydroxide. Okay, so calcium hydroxide plus silica, this is polyorganic materials, plus water, we get CSH. Okay, to remove calcium hydroxide, densify the structure, reduce the porosity. So as a result, durability will be higher. Also reduce the temperature rise, so thermal cracking is reduced. For workability and cohesiveness, in general, it will be improved, but for silica film, that may be the exception. Okay. It will generally also reduce bleeding, segregation, make the concrete more homogeneous. Okay. Ultimate strength will be improved. Okay, so these are some of the questions, the idea, think about after the class. So what's the difference between the flash, silica film, and slag? You can think this question based on chemical composition and also size of these materials. Okay, so for flash, we have a class C and a class F, and how we can how we define the class C and the class F. So basically, class C flash is the flash with more than 10% of calcium oxide. Okay. So how do pozzolan influence mechanical properties and also flash properties, as well as the durability of the concrete? All right, so I will try to get our first homework ready next week. Okay. Oh, so how many of you has get your textbook? Okay.